Morning.
Huh. Where to stay?
Is it recording? It's working, yay. Okay, wanna start?
Let's just move this slide.
Okay.
All right.
Hello. All right, welcome everybody. Thanks for coming. I know it's middle of the week and it's late and everyone's tired, so I appreciate it. Hopefully you'll find this helpful. We'll go over like everything in topic 2 in full depth. And then Yago's got to go at 7, but if you have questions, I'll stay a little bit after if you have any questions, but you can ask as we go. Like you don't have to like wait for us and then like, wait till the end. You can just ask questions. And if it's related to like problem set, topic notes, anything, that's what we're here for, just clearing up any confusion, because it's due, problem set is due what, tonight, right? Okay, yeah, so let's get any confusion like out of the way before we turn it in, so.
Good.
Yeah. Just click.
All right, so these are just some of the things we're going to be going over tonight. What affects protein folding, the heat shock response in UPR, protein function and regulation, enzyme function and mechanism, and then the regulation of protein function. So first, what affects protein folding? Does anyone know? I know it says it up here, but can anyone describe how proteins fold? Like what interactions happen with protein folding? Or what level of structure is protein folding? I mean, I guess all of them, yeah. So we know primary, right? Just the chain of amino acids. Secondary is backbone interactions, only backbone, no R groups in that, right? Then tertiary is the R group interactions, more of like the 3D form. And then quaternary, does anyone know quaternary? How it's different than tertiary? It's multiple chains, right? So what can break those things? What can unfold a protein? We have thermal energy, so heat, light energy, pH, and salt. So way I think of that is, for example, say you get a sunburn. So from light and heat, the reason a sunburn is bad and the reason sunburns can give you skin cancer is because protein unfolding. Another thing, when you cook an egg whites are a bunch of proteins, right? As you cook them, before you start cooking them, they're just clear, right? And then as you cook it, you see it turn white and it solidifies. That's because the proteins are kind of unfolding and getting all clumped together, which we'll talk about here in aggregation. So just remember these environmental factors and how those will unfold proteins. So we have denaturation. That's one of the processes of misfolding. When this happens, they can they can come together, refold again, as long as they haven't aggregated and formed a clump. And like I talked about, aggregation is just a clump of those proteins that were all misfolded. Like when you cook the egg, they all clump together, turns kind of solid. And once you have that chunk, you can't really take them apart and refold everything. And then chaperone proteins are proteins that help other proteins refold. All right. Any questions on that? All right. So again, this just describes these environmental factors and how they drive the misfolding. When you have the increased heat, the molecules are moving around more quickly because of the kinetic energy, and the bonds aren't as stable. So they kind of just break apart and everything unfolds. The opposite, when you have too little heat, then they're too stable because they're not moving around a lot. And that leads us to the Goldilocks hypothesis, which means being more stable isn't always better. You want to have like an intermediate stability. If it's too stable, they're just gonna stay put, not really move around. The electrons aren't gonna flow. If you have it not stable enough, they're just gonna break apart and not hold together. So examples of light energy, like UV rays and lasers, it's kind of the same, works almost the same way as thermal energy. They just disrupt the bonds in between the molecules. And then pH and salts. Again, these are a little bit different because I don't know how many of you guys took chem or know this from chem, but pH will affect the charges on different atoms. Same with salts. Salts will have charges. So that's like adding charges to the solution, and that'll interact with already charged things. So for example, DNA, you guys know the backbone of DNA with the phosphate groups is negatively charged. So say you add positively charged stuff to that, it's going to interact with the backbone and kind of separate it, if that makes sense. Yeah. And then here's a quick question. So I'll ask the question. I'll give you guys some time to think about it and talk to each other if you want. And then I'll ask for volunteers to share their answers. All right. So what levels of protein structure are affected by a moderately high increase in temperature? All right. So take a few minutes. This is like what we talked about. It's either looking for primary, secondary, tertiary, or quaternary. All right, we think we got to figure it out. Any volunteers?
Secondary, tertiary, and quaternary affected by it.
You think you can go a little more in depth?
Because temperature, thermal energy, and it makes the non-covalent bonds vibrate more, or the vibrate more.
Yeah.
It vibrates so much that they like.
Okay, perfect. And then why wouldn't it affect the primary?
Because primary is connected by the.
Okay. Perfect. Exactly. So that's the key. Yeah. You have to know the strength of the bonds. Peptide bonds are covalent, so they're stronger. So it wouldn't be as affected. So you would still get the chain of the amino acids in their original sequence, but they wouldn't be folded all together. No backbone interactions, no R group interactions. Make sense? Perfect. All right, so now the heat shock response in UPR. For the heat shock response, this can happen as a response to too much heat, like the name says, too much light energy, stuff like that. It happens mainly in the cytosol. So misfolded proteins are sensed there, and they're sent to the proteasome. And you guys all know what the proteasome does. The proteasome is kind of like the garbage disposal of the cell. So all the misfolded stuff will go there, and it'll be broken up and reused for something else. In this response, chaperone proteins are upregulated because these chaperone proteins kind of help control the problem. They can help refold proteins, or they can tag proteins to be sent to the proteasome so that they can be destroyed. So by upregulating those, the control of misfolded proteins is made easier. And then for the unfolded protein response, this is a little different. This begins in the ER. Does everyone know where the ER is? The endoplasmic reticulum, right? So the misfolded proteins are sensed here, and then chaperones are upregulated again for the same reason, to tag them. and send them to the proteasome. But here translation is deregulated. Can anyone think why translation would be deregulated? Exactly. So the cell already has the problem of having too many misfolded proteins. So obviously something's wrong with the cell, something's going on. If you keep doing translation, and remember, translation is the process of turning the mRNA sequence into proteins. So it's making proteins. If you keep doing translation, you're going to keep getting more proteins that are misfolded, and it's going to be a big problem. And also, even if it's folding them right, it's using up time and energy for that when you want to fix the problem that you already have of the misfolded proteins, right? So it kind of slows down translation so it can focus on the main problem. And then, yeah, once the proteins in the ER get ubiquitinated, which it just basically means it's a post-translational modification with a ubiquitin group is added to it. And that is basically like a signal. Like say you have a letter in the mail and you put the address on it. That's basically what it is. It's the address to where it's going to go. So it knows to go to the proteasome. Makes sense. Yeah, and then retrotranslocation is just misfolded proteins from the ER and their path to the proteasome to be broken down.
Okay, so protein function and mechanism. All right, so this is like all of the enzyme stuff, like ligand, substrate. In this case, ligand is a ligand. The protein is the substrate. Some people get that confused. The substrate in this case is the protein. So again, we talked about the Goldilocks thing. So things need to be just right. And the same thing applies to ligands and their substrates. So each ligand and substrate complex are specific to each other. So it's like a lock and key, right? So one ligand isn't necessarily going to fit into a certain kind of protein and vice versa, because they need to be very specific to each other. That's the Goldilocks hypothesis, which is everything needs to be just right. And you're going to hear her say this over and over and over again. If you remember, there was a question in class. Do you guys remember it was like the 30 Celsius and like the 37 and like which one would be better? And the answer was you have to do the experiment to find out, because everything has to be just right. There could be environmental factors. There's no straight answer, basically. So everything is specific to each other is what I'm trying to say. And now let's talk a little bit about Katie, because this is kind of tripping some people up. She went over the equation in class with you, but let's just kind of break it down a little bit. So again, affinity. When we talk about affinity, to simplify it, is how much a ligand and the substrate like each other. Do they want to stick onto each other? Do they want to let go of each other? How much that is the affinity. So if something is high affinity, it really wants to stick together. Something is low affinity, it wants to get away. So why does it make sense that they form non-covalent bonds when they bond together? Does anybody know why? Yes, they have to get away from each other. So ligand goes into the substrate, enzymes do their thing, reaction happens, that product needs to be released. And because non-covalent bonds are weaker than the covalent bonds, it lets us do that easily, right? Because we don't want them to stick together forever. We want them to come in, bind, do their job, and leave. And so that's why it makes sense that there's non-covalent bonds happening. So cell is a dynamic place. Things are always changing. Things are always adjusting. So we need to be able to change things whenever we want to. So the non-covalent bonds, when they break, they're easier to break, they're easier to form. Let us do all of that changing stuff. Does that make sense? Yeah.
What is an example of low affinity behavior?
Low affinity. So that's actually what I was just talking about, right? So again, affinity is how much two things like to stick to each other, right? So when we do stuff with enzymes, the enzymes, they come in, they do a job, and they have a product at the end of that. That product is the ligand. But we don't want those two to stick together forever. We want to release that product so that product can go and do whatever it needs to do. In that case, would it be better if we need to let the product go to have lower affinity or higher affinity?
So you only want low affinity when it's a product.
Right. So remember we talked about, we'll get into like conformational shifts and like what that all means and like how this happens in a bit, but like brief overview is when something like two things bind together, the shape of that complex changes. So the chemistry is being changed. And when the shape changes, when the structure changes, what changes? Function. So we'll get into that in a bit. So what determines the KD of a protein-protein ligand interaction? So there's three things. there's the architecture of the bonds, and this is a question on your problem set, hint. Architecture of the bonds, the number of bonds, and the shape and size. So the bonds, we're talking about bonds, we're talking about the bonds formed between the atoms on the ligand and the atoms on the amino acids in the binding pocket of the protein. That's just a fancy way of saying wherever the ligand is sticking to in the protein. Yes. Yes, and we'll get into that. So that's what the chemistry of the R groups, which is actually the next slide. So when talking about R groups, the size and chemistry matters. If she asks, okay, what is like the strength of these bonds? What is like the KD if we didn't have much information and we just had information about the chemistry of the R groups or like what the R groups are, like a lysine or glutamine, whatever. Look at two things. One is the size and one is the chemistry. So when you know size and chemistry, these fancy things like the architecture of the bonds, the number of bonds, that becomes a lot clearer because we know if something likes to bond to each other more than another thing, right? Does that kind of make sense? We'll get more into it, but any questions? Yeah.
Architecture, like the orientation is.
Yeah, right, exactly. So like, let's say you have an R group, but it's maybe too big to like correctly fit in with everything else. That would kind of affect, even if it can bond, might affect the strength of that bond altogether. So when we say KD is a measure of the half-bound state, what does this mean? Can somebody answer this for me? And I'll do a little demonstration after, but can somebody kind of briefly explain that? Half-bound state, what does that mean?
Like 50% of the protein is bound in complex with the ligand, which means that like what's left is like your cake.
Yes, exactly. Okay, so can we put the screens up so I can like try? Or do we have to turn on?
You wanna do it on there?
Yeah, I'll just do it on there. So this really helped me out when I was taking this class to see like a visual thing, so I'm more of a visual thinker. So let's take 6 proteins, right? Right, 6. Okay, let's say I put a concentration of, let's say 60. That's what you're gonna see for the units into the system. Now, I'm getting in ligand, half of the ligand. I'm sorry, not half of the ligand, but ligand is sticking to 3 out of the 6, which is half of all the proteins that I have. That concentration is my KD. So the fancy like equation that she was showing you and everything, it's just a way of saying this all has to do with affinity. So KD and affinity are related how? Inversely or in a like, does anyone know? Inversely. Okay, why is that? So, okay, affinity is what? How much two things want to stick to each other, right? High affinity, they really want to stick to each other. Low affinity, they really want to get apart. So, if we have, instead of 60, let's say we reach KD, reach the half-bound state at 20. Do we think that that ligand really likes to stick to those proteins or they don't like to stick to those proteins? If we just need 20 to get to the half-bound state. They like it or they don't like it? Thumbs up or thumbs up? Just give me a quick. Thumbs down, thumbs up. Okay, I'm seeing a little bit of both. So the less concentration that I need to get half of these bound up means that I have a higher affinity. So again, they're inversely related, have that in your head. So if you have a question on that, you can kind of work on it. So you know that it's inversely related. The less ligand concentration I need to put into the cell to fill up half of these, the better they like it. If it takes me more concentration to fill up half of these, same number, right? Then they probably don't stick to each other. Does that make sense a little bit more? Is that kind of helpful at least? I like seeing it visually because I'm not really good with the equation stuff. But how much concentration do we need to fill up half of the proteins that we have? What are some things that we could do to kind of like mess with the KD? Like, what are things that we could do to change this? Actually, let's do this question first. If a protein is changed that has lower KD for its substrate, will it have increased or decreased affinity? Increased. Can somebody explain? Oh yeah. Yep.
All right, I have one quick thing for how I remembered KD. So the D stands for dissociation and think of K for constant, right? everyone knows what dissociation is, right? Separating, right? So a higher KD, higher dissociation constant, means the things dissociate easier. So if they separate easier, they have a low affinity. So high KD, high dissociation, low affinity. Low KD, low dissociation, they stay together more, higher affinity. Make sense?
Perfect. Okay, so we said increased affinity. Why? So yeah, it's literally what he just said. So if KD is a measure of the dissociation between a protein and a substrate, I think I got that wrong, but the higher KD, it's the more likely something's going to dissociate, what he just said. If we have lower KD, we are less likely to. So if they're less likely to go apart from each other, that means they like each other more. They like sticking together more. Are we good on that concept? Okay. So enzymes. So the main function of enzymes is to lower the activation energy. Do we know, can somebody define for me what activation energy is? How much energy you need to get the reaction going. So that's the hill. When she talks about the hill, that's just like how much we need to like get the reaction going. Can anybody tell me, like, on this graph, where is the transition state? Where is it on this graph? Top of the hill. Okay. So when we say stabilize energy, we really just mean lowering energy. Whenever you see the word stabilize, just think lower. Okay. So the enzymes lower the amount of energy that we need to get that reaction going. Why is this a good thing? Speeds it up. Yep. What else? What else? Less effort, right? Everything in the cell is about efficiency. So if we can do something with less energy, we're going to do it, right? That's why enzymes are so great. They speed things up. Does it mean that the reaction is not going to happen? No, but it means that we can do it with less energy needed to get that going. Does that make sense?
Think of the graph kind of like a road, right? So you can be driving your car and you can go up that steep road. Either way you can make it. It'll go slow at first. If you add an enzyme, it brings the top of the road down and it makes it easier to get to the end. Make sense?
Yeah. So in the figure, it gives you an example of like a spontaneous / exergonic reaction. So the reactants are up here, products are down here. The opposite, the non-spontaneous and endergonic, where's the product going to be? Up there? The reactant's going to be down here. That's all that is. Okay. So if you need an example of the exergonic, it's right here. I also think like I think like exit almost. So like it ends at a less of a place. That's how I remember it. And then the other one is just the opposite. But that's what those two means.
Or you can remember exer means energy out. So if you have a lot of energy at the beginning and then less at the end, that means energy left. And ender, in, energy in. So you had a little bit at the beginning, a lot at the end, you had to put energy in to get to that.
Any questions on that? Cool. So enzymes, what we were just talking about. So the enzymes bind to the substrate and they remain unchanged at the end of reaction. What does that mean? What do I mean when I say the enzymes remained unchanged at the end of the reaction? If I gave you a question that said, tell me what changes in this reaction, should I say that the energy of the enzymes change in this reaction? No, the enzymes are just doing the job. They're just there to do the job. But nothing about the actual energy of those are changing through this entire process. So again, somebody recap for me, and I'm putting this here over and over again in this presentation because I really want to hammer this concept in, but why should we not have affinity for the product? So, right, so the substrate, it goes in, this happens, and now we have the product. That's this. That's what you were asking about earlier. Why should we not have good affinity for this product that we just made? Somebody recap for me. Right, we don't want it anymore. We did the job, we're leaving it. Okay, so just make sure you hammer that in. Ribozymes made of RNA protein, it's just like a ribosome enzyme. Not much there, but I think that word is in the problem set somewhere. Yeah.
All right. So different ways of regulating protein function. There's allostery. Can anyone describe allostery in their own words? exactly. So like Laura was saying, protein shape dictates function. So if you change the shape, changes the function. Where's an is there an example? Yeah, so you see here if there's a different shape, like, can you guys see? Yeah. So here it's the right shape for the ligand to go and bind. But then here, if it changes shape, it can't go in and bind. So if somehow you change the shape, the function will change. And then there's dimerization, which is two things coming together to form a unit. You guys will see examples of this in later pathways in the class. So just remember that word. You'll have, there's no example. Oh yeah, right here. So you'll have these go in and then put these two units together and make the reaction happen. Make sense? All right. You want me to do this one too, right? Yeah. Then post-translational modifications. Like the name says, these are changes after translation. And again, translation, remember, is mRNA being made into the protein. There's a question on the problem set that asks if they're reversible or irreversible, I think. What does everyone think? Reversible or irreversible, or both? Reversible? So there's both. Most are reversible. And why do we think most are reversible? Yeah, exactly. It like turns things on and off. Does anyone know a good example of something that we need to turn on and off? Think of phosphate, adding and removing a phosphate, GTP to GDP, right? So that's an example. Phosphorylation is one of the examples. So in GTP, you have 3 phosphates. You want to take one off to make GDP. And then again, to make GTP from GDP, you want to add a phosphate. So those are all reversible. Yeah.
I just want to add this just because we were talking about this a lot in like office hours today. So there's a couple phrases that you're going to hear over and over again and what she's trying to hammer into you. So the first one is the conformational switch or conformational, what was it? Shift. That's what it was. That just means shape change, right? That's what that means. Switch mechanism. When we say switch mechanism, let's like the example that we just used. So phosphorylation and dephosphorylation. So phosphorylation is adding a phosphate, dephosphorylation is taking it off, right? So when we add that phosphate to something, we change the chemistry of that complex now. Now there's like new stuff in there. We're changing the complex. We're changing its structure. And when you change structure, change function. So when it comes to turning things on and off, you could do that by adding a phosphate onto something. So that maybe turns it on or off, however it works. And then you take away that thing, and now you're back to that previous state. So that question on your problem set where it's like, is it reversible, irreversible? You can reverse or start a process by adding something or taking something away or changing it however else you will. But that's what we mean by like switch mechanism. By adding a phosphate, this is just an example, adding a phosphate or taking off one, you are creating your own switch mechanism. You're creating your own on and off switch, essentially, right? And that's what you'll learn with like the GTP and GDP, which she's about to talk about.
No, that goes with the reversibility. So you'll want certain strength bonds for ones that are reversible and certain strength for irreversible. Because if it's irreversible, you're taking it off and on. So it should be a weaker bond compared to the reversible.
What would be the example of the irreversible?
So-
There is.
Okay, so first, an example of an irreversible is cleavage. So you guys will have, there'll be some proteins that are made that have like a tail portion, and to be activated, part of that tail needs to be cleaved. So you cleave it and you don't want it to go back on because then it won't work. Remember, it's like as soon as it's cleaved, the protein starts working. And so yeah, that's one. Cleavage can also happen to like turn off a protein. So you'll cleave it and you don't want it to go back on. So then it won't go back. And what was this? What was the
Like,
other?
why it's
Oh,
not
why?
the
Yeah. Because what happens before translation? What do you have before translation? You just have the mRNA chain. So that's not, it doesn't really like have a function yet. So say you put a phosphate group on an mRNA chain, like it wouldn't do anything. The mRNA is just the code to make the protein. And then once you have the protein, then you want that protein to get a signal, like one of these post-translational modifications to go do something different. But if you just put it on the mRNA before, it doesn't have a function, so it wouldn't do anything. And it would screw up the reading probably of the ribosome to make the protein when it reads the mRNA. Make sense? You're gonna say? And then last step, nucleotide binding and hydrolysis. So this is the conversion of ATP to G, this is swapped, but ATP to ADP and GTP to GDP.
It's two.
All right. Yeah. So hydrolyzation is just the taking away of a phosphate, right? So remember, ATP and GTP are, the T is tri, the P is phosphate, right? So 3 phosphate groups. Then ADP, GDP, diphosphate. So 2. So when you go from ATP to ADP, you're taking away a phosphate group, and when you go from ADP to ATP, you're adding. Make sense? The enzymes that do this are called ATPases and GTPases. Those will help turn ATP or GTP, like in the name, to ADP or GDP. Make sense? Not the other way around. So if the name ATPase, you start with ATP. GTPase, you start with GTP. And then you go to the DP. Make sense? All right.
Yeah, we have some questions.
All right, yeah. And then here's some questions. What are the names? This is important to remember and can be confusing. So make sure you're paying attention on this question. What are the names of enzymes that add or remove phosphate groups from substrates? Kinase adds, right? Phosphatase removes. What's the process of adding called? Phosphorylation. And the process of removing? Dephosphorylation. Okay. So just because you get that now and it seems easy now doesn't mean you won't forget it on the exam. Like this is an easy thing to confuse. So make sure you really understand the naming and you're not kind of just lucky guessing it one time. All right. And there, it says it right there. All right. Give an example of how a post-translational modification can cause a conformational shift, which in turn changes the function of the protein.
It's a lot of words, but it's simpler than you think.
protein
And what would we call that?
phosphorylation.
Anything else? There's multiple answers to this. There's a lot of them. Ubiquitin, right?
To get it.
Right, because we want it gone, right? Can you actually, okay, let's go a little bit more, like why does it matter if we put a phosphate on something?
Like, yeah, how does it change the conformation? Exactly. So everyone know what charge a phosphate group has? Negative charge. So if you're adding a negative charge to that protein, say the protein has other negative or positively charged portions, what would happen? It would move around, right? If it has negative charge, it would move away from it because they repel. If it has positive charge, they're attracted, so it would move together. But either way, it would change the shape of the protein. And again, changing the shape changes function, right?
Yeah, and when you hear the word like surface chemistry, that's what she means. So like if two things are interacting, surface chemistry is changed, and then that changes the structure, and then that changes the function.
Does everyone have the answer for that one down?
So really just hammer in, like, conformational shift means you're changing the shape. Which also can be used in a switch mechanism, right? To turn something on or off. That's what switch mechanism is. And at the end of the day, change the structure of something, you change its function, right? Yeah, that's it. We'll stick around for a bit if you guys have any more questions, but does anyone have any like non-specific questions right now on any of the concepts? Okay, cool. Well, thanks for coming. We'll stick around for a bit if you have any like more specific questions. But we'll send out these slides. We've tried recording it too, so hopefully we'll be able to send that out as well. Thanks for coming, guys. Oh yeah, she has a question. Hold on a second. Yeah.
Anjali, how do I stop this? Mm-hmm.
No,
Yeah. So.